right, so we can start. So what we are discussing is the broad topic of delays in devices and circuits, but along the discussion, if we encounter something interesting, then we take a detour and start looking at that also, right? There is no fixed syllabus in this particular course. Whatever I feel, and if you also feel that you require some discussion, we can take it up, right? So one of the things that came up in the last lecture was this reverse leakage current. So let me spend a little bit of time to reverse leakage current. Reverse leakage current in a PN junction. And it gives us an opportunity to talk about a very basic phenomena in semiconductors, which is thermal generation rate. Thermal generation rate, that if you have conduction band, EC, all of you know that EV carriers are continuously, electrons and holes are continuously being created, right? Generation rate is there, and so there is a generation here, and there is of course recombination here. This is a very basic phenomena that's all the time occurring inside the semiconductor. Generation, recombination, right? Now in semiconductor equations, where do you see the term generation rate? Where does it enter? See, Poisson's equation. If I write, so there are basic semiconductor equations, right? Semiconductor equations. One is the Poisson's equation, del square psi by del x square minus rho by epsilon, right? Poisson's equation, very basic equation. Solving any semiconductor problem basically boils down to solving a set of equations with a set of boundary conditions. Right, so Poisson's equation is a very basic equation. Almost everywhere you find that to solve the problem and to understand it, you'll have to use the Poisson's equation. What else is there? Which other equation? That's Gauss law. Poisson's equation is Gauss law. It's coming from here. Del dot D equal to rho. Right, so it's coming from there only. Poisson's equation. What else is there? Continuity equation. All right, so how do we write continuity equation? Let's say if I want to write it for electrons. Continuity equation tells us what? Del N by del T equal to? So what does continuity equation, what is it describing? So this as you're saying, this equation is relating electric field to charge. Basically a relationship between charge and electric field. Right? Electrostatic, there's a charge, so a charge here and the electrostatic electric field, how it is related to the charge here. So that's a basic equation, relationship between charge and electric field. What does this equation, continuity equation that you just mentioned, what does it represent? One over Q del Jn by del X plus Gn minus Rn. Right? Why is it, these are basic equations. You guys should just, moment somebody says continuity, you said yes. You know, immediately you should reel-off all the terms. It's so basic to semiconductors. Without that, you can't solve PN junction, you can't solve bipolar, you know, many places, solar cells, LEDs, everywhere continuity equation is entering. What does this equation represent? Del N by del T equal to 1 over Q del Gn by del X plus, and similarly you can write for holes also, right? You can write for holes also, del P by del T, a similar equation. What does it represent? Continuity equation.
Concentration change.
Yes, change in electron, right, left hand side is change in electron density at a certain point, right? But what would you like to call it? For example, it is a general term for all these is that this is a conservation equation.
Conservation of charge.
Conservation of not really charge, conservation of electrons. This is for conservation of electrons, and the other one is conservation of holes. Charge would then you will have to combine both electrons and holes and all that, and then you write conservation of charge. It's a conservation equation. Conservation equation, like all of you know, conservation of energy, right? Amount of energy that you add versus amount of energy that you take out, and all that energy cannot be destroyed, or is that kind, right? So it's the same thing. The increase in electron density at any place, what can it come about because of? An increase in electron density in a place. Let's say if I look at this one here, a particular point, if I focus, how can electron density here increase? We are talking about this del N by del T. How can it increase? What are the different mechanisms? Huh? So generation can cause an increase in electron density. So and recombination will cause a decrease. So that these two terms are clear. Generation will increase, recombination will decrease. What does this represent?
So this is some kind of current gradient.
Right, so Gn. So it means if more electrons are coming in, and let's say more electrons are coming in and less are going out, then the difference between the two will give rise to an accumulation of carriers here. Right, so the gradient of current will give rise to another source for change in electron density at this point. So this gradient in current, generation rate, and recombination rate. This is a conservation equation. These are the only three things that can cause a change in electron density at a particular point. So continuity equation is just very simple. Just how many electrons are coming in into that particular region, how many electrons are being generated in that particular region, and how many electrons are recombined. That's all. You're just counting the number of electrons, right? It's a balance equation, just counting that. So this is the place where you find the generation term enters here. In this particular equation, generation term or recombination term, they enter into this particular equation here, right? By affecting the electron density, obviously they will affect the electron current and everything else inside this thing here. So it's a very fundamental process, generation. So what we were discussing in the last lecture is that when we look at a p-n junction, we were looking at a p plus n junction here, and we draw a depletion region. Let me draw a depletion region a little bit bigger. X equal to 0 and x equal to xn, let's say. We were talking about, for a moment, reverse bias. So this is ground, and let's say I apply a reverse bias. Right, and just for the sake of discussion, I have some numbers. So we'll consider a reverse bias of -1 volt. And we'll consider here a doping density of 10^16. So that we can get some numbers here. So we were saying that reverse current is due to thermal generation. Generation is occurring and is generating electron and hole pairs. For example, this is very easy to see here. Electron hole pairs are generated here. The holes are going to go here. The electrons are going to go here. Right? The field is like this. Right? So it's very easy to see. Any electron hole pair which is generated is separated by the field, and they go in the opposite direction and give rise to the reverse current. In this case, it's a little bit harder to see. You generate an electron and a hole, but we said the moment you apply a negative bias here, you create a boundary condition here. You create a boundary condition, and so you are creating a hole density, excess hole density, del P equal to, or hole density equal to 0 here. A very small hole density. So what happens is the holes start, because if you've created a place where hole density is almost equal to 0, so the holes start moving here into that particular region. It establishes a gradient. Right, so here also an electron hole pair is generated, the hole goes here, the electron goes here. So two sources of reverse current is there. Reverse current is due to thermal generation, and the two distinct sources are within depletion region and outside depletion region. These are the two distinct regions. Generation is occurring inside the depletion region, generation is occurring outside the depletion region. Both are contributing to current. So then what we need to understand is this term, the thermal generation. Right? I mean, we say thermal generation rate, but the thermal generation rate here, the rate I'm talking about, rate. So what are the units of this? Number of carriers generated per centimeter cube per second. Right? This is the units. The rate, number of electron hole pairs that are generated per unit volume per unit time. Right? So the rate at which the carriers are being generated here and here are different. It's the same thermal process, same semiconductor, but the thermal generation rate is very different outside the region and inside the depletion region. And these processes are all understood through, as I said, is Shockley-Holroyd recombination, SHR model. This is the model which explains how generation and recombination occurs in silicon. This is the dominant mechanism. There are others that are there, but they are much less important. This is the most dominant mechanism of this thing here. And one of the key things about this particular model is, what it says is that generation and recombination occurs via defect. It's not a direct process, it's an indirect. So if I'm looking at generation, so what is really happening in generation is, if you think about it, an electron is going here into this intermediate level. And then from here, it is going here. So when an electron goes here, what you end up with is, you're getting a hole. And then you end up with getting an electron. So look at the generation is not a single step process. I mean, not simply an electron going into the conduction band. This is not how it is happening. It is happening via these impurities. Impurities and defect levels, they play a central role in how carriers are generated. Thermal generation and how carriers recombine. So very, very important role that they play. Now you have to go into, suppose, so very important point that I'm trying to emphasize is the thermal generation rate is not a constant. It's not a constant. It's not that you say, oh, this is the rate at which carriers are being thermally generated everywhere. No, the thermal generation rate depends. So a very simple model for thermal generation rate is, if you have a defect right in the middle, let's say, then you can show that thermal recombination or generation recombination rate goes as Pn minus Ni square n plus P plus 2Ni divided by 1 over tau. The generation, if Pn, if the product of Pn is greater than Ni square, what you have is recombination. You have recombination, which means the product of holes and electrons is more than Ni square. So you have recombination and generation, net recombination and generation will only occur if you have non-equilibrium. At equilibrium, what will you get? P times N is equal to Ni square. So you don't have any net generation or net recombination. I mean, there is a generation going on, there's a recombination going on, but they are cancelling each other. Okay? So Pn minus Ni square over N plus P plus 2Ni. So if you want to understand this, then you have to look into this equation here. A very simple equation which will give you lots of insight into how So what we are talking about is a net. Note that this is a net generation rate or a net recombination rate, either way. So we are talking about, if I go back into continuity equation, I'm taking a difference of the two. I'm talking about that. Okay, because this is the more important term here. What is it? If there's a generation also occurring, there's a recombination occur, then I have to look at the difference. What is the net generation rate? What is the net recombination rate, right? If this term is positive, then I have a net generation rate. If this term is negative, then I have a recombination, right? So it's that only. So this is all being understood by through this equation, very simple equation that you can take. Pn minus ni square over n plus p plus 2ni over 1 over tau. Tau is recombination lifetime, and it depends on the level, the impurity characteristics here. Tau is determined by how many impurities are there and the other characteristics of the impurity. Number of number of trap levels or impurity, if you would like, Ni. Ni would be confusing, so I'm calling it a trap level, let's say. Trap or a recombination level, NT. Plus other characteristics of the defect that is there here. So lifetime depends on that. So it's totally controlled by the impurities and defects which are causing recombination. So note that if you want to understand the net generation or recombination rate, you have to look at Pn minus Ni square n plus p plus 2Ni over 1 over tau. So, let's come back again here. P plus, and we are talking about recombination depletion region and outside. Right, so, and we are talking about this equation, G equal to Np minus Ni square n plus p plus 2Ni over tau. Now, when you are talking about reverse bias, what it does, it makes Np much less than Ni square. That's what it ends up doing it. Either I look here inside or I look here outside the depletion region. What happens is the product of N and P becomes lower. On the other hand, when you apply forward bias, then Np becomes much larger. That you are injecting electrons and holes, right? So Np becomes much larger than Ni square. In reverse bias, Np will become much smaller than Ni square. So that's the first thing. So what you can do is generation rate, you can approximate it as minus Ni square over n plus p plus 2Ni times 1 over tau. That's where you see negative sign, which means it is generation. All right. So if I would log, I will call it R. Here R recombination rates, and so R equal to minus, and minus R will become basically equal to generation rate. Okay. So G equal to Ni square n plus p plus 2Ni by 1 over tau. That's the generation rate. So now you look at the generation rate here outside the depletion region. Let's say, let me call it G out. So G out will be what? If I look at outside the depletion region, what is the electron density? It's n-type, doping, electron density is very high, Nd. This is equal to Nd. P is small, and Ni is obviously much smaller than this thing. So what happens to the generation rate? Ni square over Nd times 1 over tau. That's the generation rate outside the depletion region. Net generation rate. Okay. So these many carriers are being generated per unit time. This thing here. So I'll give you some numbers so that we'll see the signal. So if I take Nd equal to 10 power 16 per unit this thing, so this comes out to be, the generation rate outside turns out to be 2.1 into 10 to the power 11 per centimeter cube per second. That's the rate at which carriers are being generated. Per unit volume, 2.1 into 10 power 11 carriers are being generated per second into this particular. That's the generation rate outside the depletion region. Now let's look at within the depletion region. Let's call this G in, inside depletion region. So inside, the first numerator is Ni square over tau is anyway. Now inside the depletion region, what do you think happens to N and P? Much smaller. N and P are very small. So what happens is, you can write this as 2Ni. N and P you can neglect. And so you get generation rate inside equal to Ni by 2 tau. A very different value, note that. Inside is Ni by 2 tau. Why is the net generation rate different? Because N and P are different inside the depletion region. N and P outside the depletion region is something else. N and P inside the depletion region is something else. Now if I calculate, if I put in the number, by the way, I'm taking tau equal to 0.1 microsecond. Recombination lifetime is 0.1 microsecond. You can take any other number, that's not an issue. So here, the generation rate for this comes out to be 7.25 into 10 power 16. Just look at the number. The generation rate outside the depletion region, 2.1 into 10 power 11 per centimeter cube per second. Generation rate inside the depletion region for the same value of tau, same tau, 0.1 microsecond, 7.25 into 10 power 16. Right? So note, 2.1 again into 10 power 11 generation rate, and generation rate here 7.25 into 10 power 16. You can put in the numbers yourself and calculate also. Just look at the difference between the net generation rate. This is all thermal generation rate. Thermal generation is so high within the depletion region. Right? The rate at which carriers are being generated, net thermal generation is so high. This is 16, so 5 orders of magnitude higher. 5 orders of magnitude higher. Right? So now we can calculate the reverse current. The reverse current due to generation inside the depletion region will be equal to what? This 7.25 into 10 power 16, this is the net generation rate, multiplied by this per unit volume. So note that, multiplied by the width of the depletion region. So this is, let's say, the depletion region width is Xn, and multiplied by Q. That will give you the net current. See if it makes sense to you. Net current density. 7.25 into 10 power 16 carriers are being generated per unit volume per second. Right? Per unit volume per second. These carriers are getting separated and giving rise to current. So Q times the generation rate multiplied by the depletion width will give you the net contribution of current to current within the depletion region. Net contribution of generation within the depletion region, how much current does it give rise to? So we multiplied by Q to get current, and we multiplied by the depletion width. And you can easily verify this thing, the units are what? Ampere per centimeter square. So this is the amount of current that I will get due to inside the depletion region. Outside the depletion region, what should I do? I will multiply it by Q times G out, multiplied by effectively what is the distance over which it acts? The whole diffusion length. Within the diffusion length, the carriers are able to reach the end here. So LP, note that LP I can calculate as square root dP by tau p. Tau p is dP by dP or tau. dP I'm taking as 10. Everything is in centimeter per second. And LP comes out to be 10 power minus 3 centimeter. So I have to multiply it by LP. So this is the contribution of current outside the depletion region. And this is the contribution for current inside the depletion region. So note that what is happening is inside the depletion region, the rate is very high. The rate is very high, but depletion width is small. Now for 1 volt, I'm applying minus 1 volt. You can easily calculate that the depletion width will come out to be for 1 volt with a doping of 10 power 16. Depletion width is 0.5 micron. Xn is approximately equal to 0.5 micron. Right, so I can now calculate how much is the contribution. Q times 7.25 into 10 power 16 multiplied by Xn will give me the contribution of generation within the depletion region. And this will give me generation outside the depletion region. So let's do that. So one term is Q G generation inside the depletion region multiplied by Xn. So this comes out to be inside the depletion region comes out to be 5.7 into 10 power minus 7 ampere per centimeter square. The other one is QG out times LP. This turns out to be this is what it comes out. Right, so this is again what we are talking about. Let me keep drawing P plus N. This is my depletion region and reverse bias, and this is what is happening. This region, all this region is contributing here, and this depletion region is contributing here. Both are contributing to current, right? Obviously your reverse current is JR is almost equal to Q generation inside the depletion region multiplied by Xn. Right? Almost the bulk of the dominant generation current, reverse leakage current is all coming from within the depletion region. Right, so the first important point to keep in mind is the net generation rate is not the same everywhere. Net generation rate is not the same everywhere, it varies. This is the equation that we are using to understand this equation here. Or this equation, then generation rate, it boils down to basically this equation here. Generation rate is very different, much higher here within the depletion region as compared to outside the depletion region. Now you may be wondering, okay, equations are giving like this. Why is it really happening? Yes?
So why have you taken NP much less than Ni square?
Because you're reverse bias. In reverse bias, see, in forward bias, you're injecting electrons. What is happening is, in forward bias, in equilibrium, you have certain amount of electrons and holes, right? You have N and P is less, and NP is equal to Ni square. When you forward bias it, you inject. So electrons increase, holes also increase, both increase. So N and P both increase. So NP will become much, much larger than Ni square. Reverse bias is the opposite. You're removing electrons and holes. So NP becomes much, much less than Ni square. So it's just the opposite of that. Okay. So, so important point to remember is that net generation rate is varying. Amount of generation that happens, net generation is different outside the depletion region and inside the depletion region. And not just simply different in small amounts, orders of magnitude different. Orders of magnitude different here. And on that basis, if we calculate the current, we find that the current is predominantly coming from generation inside the depletion region and not outside the depletion region. Outside the depletion region is considerably smaller. All right, so that's this thing here. Now, if you're wondering why is it happening, why is this generation rate depending on the N and P and all that? All right, so if you want to that, then basically, as I said, just keep in mind that how is recombination, how is generation occurring? You have EC and EV, and you have a level, right? Again, how generation will occur, how an electron from here will go here, and then once it comes here, it goes here, right? That's how generation is occurring. So imagine if I take my semiconductor and I look at this region. Why? So what we are trying to answer is, without going into the details, why is generation outside the depletion region here so much smaller than here inside the depletion? Why is it? Without going into the equations. If you just go with the simple model, how is my generation occurring? There's a defect level. Electrons are going from valence band to the defect level and then from the defect level up. So if you look at this point here, what is happening in this region? This region has lots of electrons already. Lots of electrons. So this region is, a lot of electrons are already there, N, right? And what will these electrons do? They will try to fill the defect level. Lots of electrons are there, they will try to fill the defect level. So what happens is, for a generation to take place, an electron has to go and find an empty level. It has difficulty finding an empty level. Now where is the empty level? Where can I go? Because a lot of them have been filled by the electrons that are there. So the first step itself that you are seeing is becoming problematic. It has to find an empty level to go into it. And those empty levels are all being filled by these electrons. Here you have 10 to the power 16 per centimeter cube. So now it's not able to find, so generation is becoming a little bit difficult. Now you come inside the depletion region. Inside the depletion region, again the same thing is there. But inside the depletion region, there are very few electrons, which means all the levels are practically empty. And so an electron that is there can go here, can go here, can go here. It can find a level there. Lots of empty levels that are there. While outside the depletion region, they're already, most of them are filled. Right? So qualitatively, you're saying, why is the generation rate different outside versus inside? Right? So you're seeing because of this, because if you just try to understand how the generation is occurring, what is the mechanism for it? Conduct from valence band, it has to go to the defect level. So it has to find an empty defect level. But the presence of all the electrons that are there here is just, outside is just filling it up. Finding an empty level becomes difficult. And so generation becomes, thermal generation becomes a problem. It's not as high as that. So that's qualitatively what is happening. Now details are, of course, you have to go into the model that we have. You have to go into the model and look at, quantitatively you have to go here, but qualitatively this is what is happening here. Right? So now a little bit you understand better as to how the thermal generation, net thermal generation rate comes about, how to calculate its value outside or inside, and why the value inside the depletion region is so much this thing here. Now related to that, let's do another set of calculation is related to something that all of you are familiar with, is a MOS capacitor. Related to this generation rate. Now how is this related to this generation rate? Okay, let me explain here. So let me draw a MOS capacitor. This is silicon dioxide. I'm going to take p-type silicon, and let's take doping as Na, as 10 to the power 17. Let's take thickness as 10 nanometer, and let's put a metal on top. metal atop, and there's a metal here, right? And we put this to ground. This is what we call as the gate. Right, all of you are familiar with this MOS capacitor. That's the basis for MOSFET. Okay. So in a MOS capacitor, what do you study? CV curve, right? So CV curve, does anybody remember? CV curve goes like this here. CV, right? And you have heard of this? Huh? This is called high frequency, low frequency, right? They keep talking about these things. Low frequency CV, high frequency CV, right? Okay. So this MOS cap and all that will have a threshold voltage. Agreed? We'll have some threshold voltage. Okay, there is a way to calculate threshold voltage. Don't worry about it. I'll just write down here phi ms plus 2 phi f plus square root. Don't worry about this. You don't know, doesn't matter. 2 phi f, C oxide prime and all that. These are standard equations. Doesn't matter. Let's say for this, metal, if I take, just to give you some number, metal work function, if I take, what have I taken? Let's see, 4.2 EV. Work function of the metal is 4.2 EV. And everything else is given, right? This is 10 nanometer. So all the information is given in this particular problem. Work function of the metal is given, and doping is given, oxide thickness is given, and you can calculate VT will come out to be around 0.5. I think if I do the calculation, 0.477 to be more accurate. .477. All right, so that's the threshold voltage. All right, and so if I apply here, let's say 3 volt, then what happens? This is larger than the threshold voltage 0.5. Then what happens? You've applied a voltage, gate voltage larger than the threshold voltage. Then there would be an inversion led, right? How much inversion led? How much is the inversion led? No, not the thickness. How much charge is there? All of you know this equation? Q inversion equal to Cox. I'm writing prime means per unit area multiplied by Vg minus Vt. Till you apply threshold voltage, what is the charge inside the device? Let's say you're increasing Vg and is going from 0 onwards and all that. Till you reach Vt, what is the charge inside?
0 depletion.
Depletion, right? So if I can write this as that before you reach, what happens is, depletion charge is there here. Once you cross Vt, most of the charge then becomes inversion charge. That is the meaning of the term Vg minus Vt. That anything above Vt, any gate voltage, note that it's a capacitor, right? So basic equation of a capacitor is delta Q equal to C times delta V. That's the basic equation of the capacitor. So if you change the gate voltage, you are going to change the charge. The issue is which charge? Where is this charge? Above threshold voltage, all charge that is created is inversion charge. All the charge that goes is inversion charge. Below threshold voltage, all the charges, roughly, approximately all the charges, depletion charge. Right? So a basic distinction. Below VT is all depletion charge. Above VT, it's all inversion charge. Mostly, predominantly, right? So if I give you VT, VT is already known 0.5, and if I say I'm applying 3 volt, so you can calculate the amount of inversion charge. How much inversion charge is there? And what is this inversion charge due to? It's because of electrons, right? And where do these electrons exist? They exist all at the surface, right? It's like a sheet of electrons, right? So now if I take Q inversion, not good. If I take Q inversion and I divide by Q, what will it give me?
Number.
Note that capacitance is what? This capacitance is per unit area multiplied by voltage. So if I divide by Q, what will I get? The number of electrons per unit area. Number of electrons per unit area. How many electrons are there per unit area? So I can easily, I've given you 0.5, I've given you 3 volt, I can do the calculation. So I need a number of electrons per unit area. Let me see if I have. Is 5.4 into 10 per 12 per centimeter square. These many electrons you require. 5.4 into 10 per 12. That's the amount of electrons per unit area. Okay? So if you, you require that. Where will these electrons come from? Where will they come from? These are minority carriers. Where will they come from?
So like, first of all, the formation of depletion region, so the electrons will jump and the semiconductor will keep on depleting.
Fine. The source of these electrons, where are they coming from?
So from the semiconductor, p-type semiconductor.
So p-type semiconductor has very little this thing. So again, why is p-type semiconductor supplying charge to this thing?
Sir, because the VG is too high here, so the band actually kind of.
No, that's okay. Bands and all that require you to it. But what is happening? Where are the holes? Where are the electrons really coming from? Huh? So again, the issue is, if I take my, let's try and understand a MOS capacitor a little bit more detail. So let's say you put this here and put this here, right? And here is where I apply 0 to 3. I apply a step 0 to 3 volt, right? I can easily do this experiment. So now what needs to happen is, note that initially, let's say 0 is, let's for the sake of argument, let's say 0 is like flat band. Okay? So 0 to 3, then what needs to happen? A depletion region needs to happen, create, right? Let's, this, by the way, how thick do you think is this semiconductor? I gave you the thickness of oxide, let's say 10 nanometer. Of course, now we are going into a few angstroms only. But how thick is the semiconductor? Right, you're making a MOSFET on this thing, and we draw at the bottom the body contact, right? How thick is this? So in this picture, I'm drawing here, this is oxide thickness, T oxide, let's say 10 nanometer. Depletion region, maybe half a micron or something like that. What is the total thickness here of the semiconductor?
So 0.5 millimeter.
So 500 micron, right? 500 or 400 micron. let's say, okay, so he gave the number 500 micron. That's the thickness of this. So the diagram is not drawn to scale at all. Right? I'm showing like this. This is a very, very thick, that is there here. All right. So everything is happening right at the surface. Right? If I take a total thickness 500 micron, everything is happening in the top 1 micron, less than top 1 micron. Okay. So don't get confused by this. So anyway, I have to create the depletion region, and I have to create the charge here, electrons. So is creation of depletion region, will it occur very fast? To create a depletion region, what do you have to do?
It will take time.
Why will it take time? Or what will determine? You've applied 3 volt. Depletion region requires you to do what?
Move charge from the semiconductor.
Charges are being pushed out, right? So which means that a hole which was here, let's say here, pushing out a hole here, and then it flows eventually and goes into positive charge here. Depletion region is also negative charge. So pushing out a hole, and the hole has to move through this resistive region here, and you can calculate the resistance of the bulk and the capacitance RC. It turns out to be very, very fast. Right? There is a resist. What prevents the holes from coming out is the resistance here. Basically, you don't have infinite current available. So it's basically the resistance here. And as I said, if you do the calculation, it will come out to be the resistance is pretty low, and the depletion region is forming very, very fast. Depletion region very quickly. Okay. If we can calculate by looking at the resistance and all that, we can calculate very, very fast. Right? It's almost like, for practical purposes, you can say instantaneously it's happening. It's that fast that is happening. But, so depletion region will form very fast, but then you have to form, because depletion region, all it requires is pushing the holes away. Right? And the holes, this thing. But you require electrons here. And electrons, where will it come from? We said, the only source of electrons in this region is thermal generation. Thermal generation. So at time t equal to 0, you've applied 3 volts at time t equal to 0. And thermal generation is what? It's a slow process. We'll see, that's why I'm doing the calculation. How slow is that particular process? I'm saying depletion region will form very quickly, picoseconds and things like that, in that range, picoseconds or even less, sub-picoseconds, something of that sort. It's that fast it will occur. But the electrons, the inversion layer, the only source of inversion layer is thermal generation, and thermal generation is a slow process. So at time t equal to 0, there's no inversion layer. Immediately after you apply 3 volt, there's no inversion layer. So what do you have then? The 3 volt that you apply here has to be dropped somewhere, right? 3 volt, the voltage has to drop. Where will it drop? It has to drop across, note that if you apply any voltage, just do a KVL, Kirchhoff's voltage law, 3 volt has to drop across the oxide and drop across the depletion region, right? So 3 volt is equal to the drop across the oxide, and if you would like, the drop across the semiconductor. These are the only 2 places the voltage can drop. The drop in the oxide depends on what? The field in the oxide. And the drop in the semiconductor depends on what? The field in the semiconductor also. The 2 fields are related together. So what happens is that there is no inversion charge, so the 3 volt is a bulk of 3 volt drop that is occurring here, because the thickness of T oxide is smaller. The bulk of 3 volt goes and gets dropped here in the semiconductor itself, the bulk of it, right? So normally, for example, if I said under normal circumstance, how much is the drop in the semiconductor? Note that voltage is 0, and the drop that you see in the semiconductor is how much? 2 phi f, if some of you remember. 2 phi f is the surface potential at inversion. How much is the value here? If you calculate, it comes out to be 0.8. The normal drop in the semiconductor is what? Roughly about 0.8. Normal drop across the semiconductor. The bulk of the drop is taken place because of the inversion charge. The drop across the semiconductor is 0.8. But when there is no inversion charge, what happens is the entire drop of 3 volt goes across this. There is no inversion charge. So what happens is depletion region is also larger. Depletion region is initially at t equal to 0 is here. But then as the inversion charge forms, then the drop in the oxide increases and depletion region starts reducing and eventually comes to the equilibrium value. So the situation is initially the depletion region is very large because there is no inversion charge, right? Almost everything starts dropping here. But as the inversion layer forms here, this drop increases and this drop falls and depletion region starts to reduce. Anyway, so this is the phenomena that is occurring. When we come to MOS and look into details, but all of you are saying thermal generation, right? Thermal generation is the source of carriers. Again, you have two different sources of thermal generation. Outside the depletion region, inside the depletion region. Which will contribute most to thermal generation? We just saw inside the depletion region is much higher than outside the depletion region. So what is contributing to formation of inversion charge is, if I can redraw here, what is happening is within the depletion region, electron hole pairs are generated and the electrons go here and the holes come here. Hole is a positive charge, eventually it comes here and eventually a positive charge goes and sits here and on the gate. It flows through the external circuit. So it is the generation inside the depletion region which is contributing to current. So now note that how much charge do I need? 5.4 into 10 power 12. I need this much charge, 5.4 into 10 power 12. These many electrons I need for inversion layer to form. What is the thermal generation rate? Well, we calculated, right? Thermal generation rate. We calculated as, where is the value? 7.25 into 10 power 16 inside the depletion region. Okay. The rate is 7.25 into 10 power 16. This is the rate number per centimeter cube per second. These many electrons I require. This is the rate at which carriers are being generated. Over how much distance are they being generated? Depletion region. Roughly depletion region, what length will you take? Say half a micron. We are doing a simple calculation, half a micron. So the total rate at which it is happening, so let's put the equation. So I require 5.4 into 10 power 12 into 10 power 12. I require this much, and this will be equal to the net generation rate, which is 7, let's say 7 times 10 power 16. 7 times 10 power 16 multiplied by half a micron, 0.5 into 10 power minus 4. This is the rate, number of carriers generated per centimeter cube per time, right? This is the thickness of the depletion region, and this is the total time that it will take to form. Rate G multiplied by the depletion width W multiplied by time, and this should give rise to 5.4 into 10 power 12. Somebody calculate how much time will it take?
So roughly 1 second.
Huh?
Roughly 1 second.
7 into 0.5 is 3.5, and 16 and 4.
5 by 3 multiplied by
12. So T is coming out to be, you're right? T is coming out to be how long will it take for, you have to wait for a second to form for the inversion layer to form. Now this will come out to be very surprising to you. Is it so slow? No, I've personally sat and taken a MOS capacitor and I've applied 3 volts to it and looked at how much time it is taking. It does take that much. In fact, it would take, in this, I'm doing the calculation for what? 0.1 microsecond lifetime. 0.1 microsecond lifetime. Imagine that if your lifetime is, let's say, 10 microsecond, how long will it take? 100 seconds or more, minutes. And I've literally waited minutes for inversion layer to form, to seeing the inversion layer. How do I know inversion layer is forming? So note that what I said was, as the inversion layer forms, the depletion width changes. So as a result of change in depletion width, what happens is capacitance changes. So externally, what I do is I measure the capacitance of a MOS capacitor. And then what I find is capacitance is changing. And when the capacitance doesn't change anymore, you know all the inversion layer is formed. So by looking at capacitance transient, you are seeing how the inversion layer is forming. And we've just done the calculation. It's taking 1 second to form. Right? So we are able to do this very simple calculation by calculating the amount of inversion charge that is required. We have the thermal generation rate inside the depletion region. We have the depletion width, and calculate the time. And the estimate of time that you're getting is a very good estimate of time. One can do more detailed calculation and all that will come out to be similar number. Right? It's a very slow process. So when you say low frequency CV, how low does your frequency have to be for inversion layer to respond? What do you think?
In hertz.
Hertz or lower? Sub-hertz, millihertz. That's where low frequency is there. Right? So you have to go to that low frequency for really to see how the inversion layer is responding. Right? So what we have done is we have gained a little bit better understanding of thermal generation. Thermal generation outside the depletion region, thermal generation inside the depletion region. What is its magnitude? How do we calculate? What are the implications of it? That's where I said here, it's a slow process. The amount of carriers that are being generated are not very large. It's given by Ni by number of, this number that I put 7 times 10 power 16 is what? Ni by 2 tau. That's the thermal generation rate. Outside the depletion region is even smaller. So Ni by 2 tau. This is the key parameter here. Right now, imagine now if you go to gallium arsenide with Eg equal to 1.4, what will happen to Ni? Maybe become even smaller, right? So you are in more trouble there in larger bandgap semiconductors, generation rate. But anyway, there are other mechanisms of generation in this that is here.
Apparently, this gallium arsenide and gallium nitride are used for RF applications, which is very.
So even your MOSFET is your inverter is switching at gigahertz. So how is it switching at gigahertz? So if the inversion layer is to switch a MOSFET on and off, or to switch a MOS capacitor on and off, you have to create an inversion layer or remove it. So if creation of inversion layer is requiring a second, how can it switch so fast? So it doesn't come from there, right? A MOSFET, if I draw a MOSFET, so this is again a lot of students carry a misconception in their mind. MOSFET is like this. There is a MOS cap. So if I were to apply gate voltage, let's say here 0 to 3, again I have to create whatever depletion region and all that. It doesn't come from thermal generation, it comes from here, from N plus. It comes from here. N plus is connected to the channel, so it just flows in from there. It doesn't, this is not the source. Thermal generation is not the source, and that's where it switches very fast. Right? A MOSFET will switch very fast. MOS capacitor will not switch fast. MOS capacitor is very, very slow. Right? So this, so as I said, we took a sort of, we went off track we were talking about delays, and we looked at thermal generation, and but our discussion is back to diode, right? In diode, if you recall, we were saying that the delay in a diode, tau, was the junction capacitance, kT by Q, by current density, and then we had the recombination lifetime. And so we were saying, if you want to make the diode fast, what you have to do is you can increase the current density and make the first term smaller, but then you'll ultimately get limited by recombination lifetime. And you can make the diode faster by making the recombination lifetime faster by introducing more defects and things like that. But we also, that's where the discussion came out, the reverse leakage current is equal to Q times the thermal generation rate, Ni by 2 tau, multiplied by the depletion width, Xn. So as you try to make tau p, low, well, if you make it low, then the leakage current here will go up here. So the price that you end up paying is the diode becomes more leaky. All right, so this basically a discussion related to reverse leakage current led us to the thermal generation. What happens as a thermal generation in these semiconductors? So the issue that comes about is, well, I don't like the fact that to make the diode faster, I have to increase the leakage current. Is there a way to avoid this? And there's a simple, this is what I want to do next for you, is there's a simple thing that, a simple calculation that we'll do. What is the mechanism by which we can make the diode faster without looking at the recombination? All right, any questions regarding what we have discussed? Okay, so the way to make the diode faster, the diode that we are talking about is like this. P plus and N is a very large diode. And we call this a diode where this is X equal to 0 and this could be X equal to L, the length of the diode. And we call this L is much larger than, or at least greater than 3 times LP and all that, right? So we call this as a long base diode. Calling this as a base region, long base diode. What you can make is a short base diode. Let's make a diode. Why make it so long? So suppose we make a diode like this. P plus and N, and now I get into a situation where this is X equal to 0 and this is the thickness of the diode, and L is, I go into the other one. L is much less than LP. Why make L such a large value? Make L much smaller than LP. Now what happens? So it's a very different diode, right? Here, as you can see here, the carrier density that you inject goes like this, and delta P goes like this. Exponentially decays and all that. Know that why this has an implication, right? Because when I wrote down the delay, tau equal to first term, and then I wrote down tau p, the second component of the delay, what was it coming about? All delays because of charge. So second component of delay was coming about because of the charge due to these holes, right? All these holes that are injected here, the holes that are stored. Now we are saying, if you make the region smaller, the amount of holes that are there in that region should become small. So the way to think about how to reduce the delay, why not make the region smaller? Why make it so thick? So that there are a lot of holes stored here. So now what will happen is, you will inject hole density, there's a depletion region here, you will inject hole density, starts from here, and the contact It's like an ohmic contact, and one of the definitions of ohmic contact is that, or an ideal contact. Let's say first of all, let's assume ideal contact. A definition of ideal contact is there is always equilibrium at ideal contact. There's always equilibrium condition, which means the excess carrier density is 0. Delta P is 0. No excess carrier density. So what happens is you get you've injected something from here and it goes like this. So the amount of charge that is there here becomes much smaller. The amount of charge stored becomes much smaller. And then we can do the calculation. It's no longer the recombination lifetime. Okay, so all right. So what we'll do is we'll do this calculation later on. So let's, as a simple calculation, maybe take out a sheet of paper. This is for class, sort of an attendance. Let's and do a simple problem. Okay, our problem. So take out a sheet, write your name, roll number. Let's do a very simple calculation. So our calculation is as follows. There is a P plus N junction. I have reverse biased it so that the depletion region width x equal to 0, depletion region width is 1 micron. And I want you to estimate what is the reverse leakage current density, GL. How much reverse current density will flow? Lifetime is 1 microsecond. And estimates. So what will be the value of J? So it will be equal to Q times the thermal generation rate, which is equal to Ni by 2 tau multiplied by the depletion width, right? That's it. So Ni, we are only talking about order. Okay, so Ni will be equal to 10 to the power 10 cell, right? So now just do and write down and sum it, so that you get an idea of a very quick estimate of how much reverse leakage current will flow in a PN junction, like this. X depletion with 1 micron. 1 micron. So do all the calculation in centimeters. 1 micron is 10 power minus 4. Ni is 10 to the power 10, yes. Exact value may be 1.45 into 10 power 10, but doesn't matter, just to quickly estimate the order of magnitude. The next thing is, it's not over. The next thing is I shine light on it. I shine light over it, and now there is an optical generation rate. And let's say all over the device carriers are being generated. The device length from here to here is 100 micron. Diffusion length is 10 micron. And the generation rate due to light, I'm shining light, so the generation rate is, let's make it, what was the generation rate for 7 times 16, right? So 17, let me make it, say 10 per 20 per centimeter cube per second. That's the generation rate. Everywhere is being generated. So it is generated here also, GOP, and is generated here also, G optical, everywhere. Right? What do you think will be the current now? Again, generation within the depletion region will contribute to current. Generation outside the depletion region will also contribute. But outside the depletion region, how much of the region will contribute? Within the diffusion length. Within the diffusion length can reach. Right? But now the generation rate, optical generation rate is the same everywhere. So optical component would be highest for depletion region, which is only 1 micron. Outside the depletion region is 10 micron. So most of the optical current is coming from outside the depletion region. Right? Most of the current will come. So how would you contribute to the light current? The light generated current would be almost equal to Q times G optical times the diffusion length. Within the diffusion length, you may generate everywhere, but within the diffusion length is only what is able to be collected. So Q times GOP times LP will be the amount of current that will now start flowing if you shine light. Depletion region will not contribute much now. The reason why thermal generation depletion region is contributing so much, because generation rate inside the depletion region is so much higher. But when you have optical, when light photon is coming, why would photon generate more electron hole pairs inside and outside? For photon, both regions are the same. So optical generation rate is the same everywhere. So for solar cells, when you go, this we are talking about, for solar cell, is the generation outside the depletion region, which is very important. And again, in many of the textbooks, you'll find something wrong. They'll say generation within the depletion region for solar cell. That you shine an electron, you shine a photon, electron hole pairs are generated, depletion region separates it out. Solar cells don't operate because of depletion region. There's very little contribution of depletion region to solar cell. It's all the generation which is outside. Outside the depletion region, the optical generation rate, carriers generated rate, they are collected and they give rise to this thing here. So you can calculate the reverse leakage current. So the first component becomes what? The dark current. The first component becomes the dark current and the second component becomes the light current when you shine the light. The dark component and the light component. Now with this example, maybe you can also see how small a light intensity can you detect? How small a GOP can you detect? Right? If GOP starts merging with the thermal generation rate, well, you can't detect that light. Right? So you are seeing how it puts a limit to your detectivity. How much light can you detect? How much power you can detect? Because you know the thermal generation rate. And for something to be detected, it has to be larger than the thermal generation rate, larger than the dark generation. If it's not larger than dark generation, you can't detect that light. Right? So if I make a statement, why do people, for good photo detectors, to detect light, why do they cool it? Why do they cool the detector?
Increase the tau.
Why do they cool the detector? So what did I make the statement? For a light to be detected, the generation rate due to it should be higher than the thermal generation rate, right? So now you want to, why are you cooling the detector? Cooling will do what? Reduce Ni. Look at that. Ni is exponentially dependent on temperature. So, when they're collecting radiation from space, these telescopes and all that, when they're trying to see their distant stars and all that, they will have detectors. And what will they do? cool the detector. And in space you have natural cooling, right? When if you James Webb telescope and all that you hear, when you send into space, the temperature in space is maybe 4 degree kelvins or whatever, very low temperature. So it's very good, very low temperature, which means Ni is very, very low. And so thermal generation is very low, so you can detect more. So, from very simple things, from these simple calculations, once you understand, you'll know, okay, this is the reason why they're cooling the detector. Because I want to reduce the thermal generation rate. How much light can I really detect? Well, GOP has to be larger than Ni by 2 tau. If it's not larger than Ni by 2 tau, then I can't. All right, so let's stop here. Please submit your sheets and